Log on, tune in, find out. Another good idea from Cambridge.
To have the second lecture by Sasha Volberg on singular integrals in bad neighborhoods. And this one is more on stochastic optimal control and sharp estimates.
Okay, so I want to explain why estimating single integrals in bad neighborhoods amounts to certain discrete analysis and lots of probability. And so, as I mentioned in the first lecture, so there are two important tools and I didn't have a chance to explain what these tools have anything to do with estimates of single integrals. So if you work with a single integral that was our quintessential example, but it can be anything else. And here x and y, by the way, were complex numbers, but it doesn't matter. So if you work with singular kernel, Calderon Zygmunt kernel, but the neighborhood where it lives is very bad, so mu is a bad measure. You are bound to have very big difficulty, and here is the difficulty. So if you want to estimate the operator with this kernel, so T has kernel K, so the most natural and the only available actually way to do that is first split this f and g to small pieces. These are like wavelet pieces. So you kind of split these things. So you should imagine that, so you split in all possible scales. So it means that here is where your measure lives, and you split this to, say, cubes q, and to cubes r. But the picture is incorrect, because q should be cubes of all scales. So because it will be a mess, I don't want to draw the picture, but you imagine that these q's are very much intersecting between each others, and r's are, say, the cubes from the same mesh, which is not necessary. You can take another mesh. And again, they are awfully intersecting between each other and also with cubes which are called q. And these functions have nice properties. First of all, these are functions concentrated on q and r correspondingly. They're almost constants. They are kind of consist of several constants each. So they're step functions with very few values. And their integrals are zeros. So there is certain constellation which we can use to estimate the kernel. But so each such piece, which will be sort of kxy delta q f x delta r g y d mu x d mu y, can be logically estimated more or less in 3 different ways. So you can estimate this in L1, this in L1, and this in L infinity. You can estimate this in L1, this in L infinity, this in L infinity. And you can estimate this in a mixed norm, L infinity in one variable, L1 in another, and like that, and symmetric. So only 4 cases. You may say, well, you can choose here different p's and q's, and why not? Well, that's because these are very simple functions. These are basically just constant functions on q and r. So the LP norms or L1 norms or L infinity norms are very close to each other. So logically, there are only these situations. And these guys are normalized in L2 mu. So in L2 mu, these pieces are somehow well normalized. So then, if you look at the texts in Calderon-Zygmunt theory, all 3 things are used, all 4 things, but 2 of them are symmetric. And this is like a simple case. This is usually used when Q and R are far from each other. And when Q and R are close to each other, this kind of cases are used. And let's see what may happen if we use these cases, especially the second one. If you use the second case, then you would need to estimate an L infinity norm, and you know it's L2 norm. And it's a sort of constant function. If you have a constant function, you have its L2 norm, and you want L infinity norm, that's the only reasonable estimate. I'll just take a constant function concentrated on Q, compute its L2 norm, and see how to compute L infinity norm. You will see that that's actually equality. The same with G. So what happens if this Q and R become not far from each other? Well, in the second situation, you will have such expressions. So it's in the second situation. In the third and symmetric fourth situation, you will have such expressions. Now, if mu is a very nice measure, like Lebesgue measure, you know how this, suppose situation Q and R look like this. This is Q, and this is almost the same size, R. It's completely harmless. It's volume this, it's just constant. Same here. And you can allow, of course, like that, no problem. Even in this case, even there is no consolation, but at least you know very well how to estimate. It can be a small denominator because Q and R can be small, but you know very well how small they are, and maybe if you sparingly use this, use it, but in very rare cases, you can still do that. So if mu is any measure, there is absolutely no way to say that this is bounded. because measure can be kind of very large here and immediately very small, very close. So for bad measures, for measures for which you have no idea how they behave, the regularity is not given, you definitely cannot use that. And you can use this and this only if Q is R inside Q. And here you only can use if, well, the other way around. Yeah. Okay. And so here this random geometric construction finds its explanation. So what you should do, you should consider such sum where there will be bad and good pairs, or rather bad and good cubes. So R is bad. Instead of writing formulas, I will just draw the pictures. If there exists Q sufficiently large, so this number is fixed. It's like 100. So it's just the definition, so it's just not a big deal. So if there is a Q which is like 100 times bigger than R, and such that here is Q, which is 100 times bigger, or more than 100 times bigger, and I will draw the bad locations of R. Well, that may be not such a bad location, but we'll put it anyway into bad, because it doesn't matter. So, so R is bad if for some Q there is such a picture. I didn't make precise how close is it here and how relatively close it is with respect to their relative length. It can be written down, but something like that. And if in this sum we add Q is good, good means not bad, and R is good, then the standard estimate works. So there are three pieces which are left from this sum.
Can you repeat the definition of R being bad?
Mm-hmm.
Can you repeat what R being bad is? Sorry.
Yeah, R is bad if there exists Q, which is like 100 times more bigger than R, and location of R with respect to Q is, I draw the pictures.
The gist of the picture is to be near the border.
Hmm?
The gist of the picture
Yes.
is for
Yeah. So yes, the R shouldn't be close to the border. Oh, actually, just because you asked the question, the goodness allows us to be very close to the border. I don't write the definition, so I can say whatever I want, but the truth is that goodness allows us such picture, but I cannot even draw what I mean. If it's close to the border, its size should be a million times smaller than the distance to the border. Okay, so it can be close to the border, but it then should be extremely small, much smaller than the distance to the border. Anyway, so if that becomes the wrong equality, because here it's TFG and here it's only good. So I should add the sum where Q is bad, R is good, Q is good, R is bad, and both are bad. And I did nothing. I knew from the very beginning that these three sums I cannot estimate. And now this, the idea is, because I cannot estimate them, I just shouldn't estimate. I don't consider them at all. So, how it can be achieved? That's the random geometric construction. It can be achieved by taking Q from one d-adic lattice, R, from another d-adic lattice, and consider the space of d-adic lattices, probability space of d-adic lattices, and taking these two d-adic lattices independent from each other. Then, by choosing this R sufficiently large, we can achieve the following wonderful small lemma, that the probability of R to be bad is very small.
Given R? A given R, because the number
Yes,
is also
yes, and this doesn't depend on R. So for any cube from, say, second d-adic lattice, the probability to be bad is extremely small if we choose this parameter sufficiently large.
And can you repeat how randomness is introduced?
Oh, in this case, very easily, because here is our measure. So we take one d-adic lattice in trivial way, and another just shift by 1/2. Yes, like that, like this.
And what put probabilities 1/2?
Yeah, yeah, yeah. And so this lemma is very simple, because what you need to now understand that to compute what is the probability of the cube to be bad, you just need to see what is the ratio of the volume of the neighborhood of the boundary with respect to the whole thing. And of course it will become small, and so that's a trivial lemma. But why it's very important here? Because roughly speaking, what is left, roughly, is f bad, tf bad, scalar g. Well, actually, there is also tg bad, scalar f, where f bad is the sum of these guys over q's which are bad. And we don't need to estimate these things, because we can bootstrap. Because of this trivial remark, we just need to notice that norm f bad in L2 mu, that's a random function. If we take the expectation, it's much smaller than norm f. We even don't need much smaller. We need like 1/4 of the norm f. Because then you just bootstrap. You just take absolute value, put here absolute value. This will be estimated. And here you will have norm t. You can say you don't know what is norm t. I have no idea. I don't care what is norm t. I know that it's a finite number. So I will get the estimate norm t from the left-hand side, less or equal good things, which I know how to estimate, plus 1/4 norm t, which I don't know, but I don't care, and then norm f, norm g, which are ones, and I'm bootstrapping and I'm done. Okay, so the only beautiful kind of remark here is that the construction is very kind of a socialistic construction, because being bad for the cube does not depend, for R, does not depend on this dyadic lattice. It depends only on this dyadic lattice. So you are bad not because you are bad, but because environment is bad. So that's what we were taught at school. So this is an example of random geometric construction where you just use two dyadic lattices independent from each other. And this allows you really forget about bad situations.
Who proposed this idea?
Hmm?
Who proposed this idea?
That appeared in the series of papers. It's started in 1997. And then there are like 10 or 15 papers of ours where we explore this idea. There is a variant of this idea which I want now to mention because it's important when we don't need two dyadic lattices. So we need a probability space of just elementary event of the probability space. Small omega and the big omega will be just one dyadic lattice, not a pair of dyadic lattices. So how we do that? So start with the absolutely not random thing. So very small mesh of intervals or cubes or whatever you want. In one-dimensional case, just very small equal intervals. If you wish, they have the size 2 to the minus n, where n is very large. And now you start to construct the probability space of dyadic lattices, where element is one dyadic lattice, not two. So what this is father. So then this is fathers. But on the other hand, this also can be father. So you flip the coin and choose which one is father. As soon as you choose one father, you choose all other fathers automatically. But next time you have two independent flip of coins. So grandfathers are already 4 choices. And you continue building like that, and you will get the probability space of dyadic lattices. And actually, the same beautiful lemma will be true. You define badness exactly as before. Only you don't have dw1 and dw2. It's just Q and R belongs to the same lattice, strangely enough. But because Q is much larger, it has so many choices to be. And so actually very few choices will make R bad. And this is what makes lemma correct. And let me mention that actually you can do it not in R1 or RD or whatever, but you can do it in the metric space. So there are so-called metric space or geometric doubling. These are very beautiful metric spaces which happen to be popular now. So these are metric spaces such that in every ball of radius 2r in this metric space, there are not more than n, well, not n, k fixed number of disjoint balls of radius r. So this is geometric doubling. So if in any ball you can fit not more than some fixed number. And then you can, in this metric space, you can do sort of the same construction of random lattices. So you start with the mesh of points, very small.
What is the singular kernel in the general?
Yeah, there are singular kernels. People already invented everything on these spaces. They have singular kernels here. So you start with a very small mesh of points, and then you want to construct the next mesh, but randomly. So roughly speaking, the model, let me just mention what is the model. Suppose you have a graph which has the following property, that every vertex has at most k neighbors. So graph with this property. And then you color the vertices of the graph. So you want to color some of them black. That's the wrong picture. You want to color some of them black, such that the distance between two blacks would be would be greater or equal than 2. The distance between every black would be greater or equal than 2. But if you have a white one, then one of the neighbor will be black. So in other words, we want to color black such that distance is big or equal than 2, but the set of blacks is maximal in the sense of inclusion. You cannot add any point. So you have a graph, and you consider all colorings which I described. And give suppose it's a finite graph, very, very large, but finite. So nothing should depend on the size. So now you consider all colorings and give the same probability to all of them. It will be just number of coloring, 1 over divided by number of colorings. And then you ask the question, given a vertex, doesn't matter which one, what is the probability that it will be black? And so the crucial thing that this probability may be small, but still strictly positive, and depends only on k. And this will allow us to repeat this construction on the metric space. Now, why I'm saying that? So let us forget for a while about metric spaces, but instead consider a couple of simple Euclidean space single integrals. So in R1, we want to consider this kernel. This is a singular kernel, but we want to spoil it. So there are several ways to spoil it. Consider such a kernel. This is a commutator, so if we call it Hilbert transform, this is the kernel of the commutator of so you compute the multiplication by function alpha and the Hilbert transform, and you get. such a kernel. But there is also another so this is a multiplicative commutator. So instead of subtracting, you consider H something like that. Multiplication by alpha, multiplication by the inverse. So this latest actually is more complicated than that, and everything from here can be applied to that one by differentiation. And so let's consider this one. And it's very easy to see that now we're asking about the following question. When the Hilbert transform is bounded from L2W to another to the same L2W, where W is something like E alpha over 2. So weighted boundedness of the Hilbert transform. Without weight, if W is 1, everybody knows that Hilbert transform is bounded. So, so here there is a long story. Actually, the question of description such weight comes from probability, because if you consider stationary process, discrete time stationary process, and you want to know when the angle between past and future is positive, the answer in terms of the spectral density of the process is exactly this. Hilbert transform should be bounded from L2W to L2W. So it's equivalent for the process that a certain statistical important property is satisfied. So why H? Well, nobody knows why. I mean, for example, during my first lecture, I considered the following operator in R2 on the complex plane. So it has a name. So as this one is called Hilbert transform, this is called Alfers-Berlin transform. And it has a beautiful property that it maps d bar of any function, C infinity with compact support, to D. So T d bar is D. So that's why this operator is in particular very important. And it plays a huge role in quasi-conformal mappings. And again, you may ask, so now everything is on the plane, so W is on the plane, about the boundedness of this operator. I actually wanted to explain why you have to ask here. It gives certain answers to questions in the quasi-conformal theory.
Or what W?
Yeah, exactly. So what is the W? Well, in both cases, it has been known for quite a while, since 70s. There's both questions, let me. And then question number 3. So take any T with Calderon-Zygmunt kernel. I even didn't introduce what is Calderon-Zygmunt kernel, but these are typical Calderon-Zygmunt kernels, and all others look approximately the same. And these are a very important class of single operators, which appear in all books of Eli Stein. Well, anyway, so these are very classical objects. So since 70s, it is known that 1 and 2 boundedness is equivalent to something which I'm going to write, and for 3 it's sufficient, and actually morally it's necessary and sufficient, so don't worry, everything is known. So and what is the condition? Here in question number 3, it can be in any RD, and for me let Q be cube or ball, doesn't matter, in R, R2, RD, whatever. So the answer is the following. You take weight. This angular brackets means you should integrate with respect to Lebesgue measure of Q and divide by the measure of Q. So it's average. Then you do the same with W minus 1. Then you take a product. Then you take a supreme. And you give a name to this. It's called A2 norm of W. It's not a norm. And the answer is that this must be finite. And this is sort of necessary and sufficient condition. So for all classical operators, it's necessary and sufficient condition. For all operators, it's sufficient condition. So this small thing, don't pay any attention. It's triviality. It's not anything deep. Now, okay, it's bounded if and only if. But how? So what is the norm? Because there is no linearity in this class, you cannot write constant times. So there is no, if it would be really a norm space and things like that, we probably would be able to prove that. So otherwise, you just take a proof, look at the proof. There are like 100 proofs, so look at 100 proofs, and you get this. Okay, so if you look at this a little bit more carefully, you get that. Now, if you really start to work hard, you get that. There was a conjecture that actually it's 1. And by trivial example, it cannot be better. It's for simple weights, you can see that if you prove this from above, it's sharp. Okay, so the answer is yes to all 3 questions. Now let me explain why stochastic optimal control and random geometric construction has anything to do with this proof of this conjecture. Now, there are like millions of people involved in the proof, so I don't know. So after all, number 3, which was the main conjecture, was proved like in July by Thomas Huttenloop. But there are many people involved, and he used the results of the people, so I want to explain a little bit. So the answer to 2 was the first obtained. It's approximately 2. So for alpha Sperling, so it was done by Stephanie Peternickel and myself. And this was done by the methods of stochastic optimal control. Now I will explain in a second sort of how we did it by stochastic optimal control. So number 1 for Hilbert transform was done later. And this is Stephanie herself. And at that time, it was much, much more difficult than for Alfred learning. Now there are proofs which show that we can do it not so much easier way, but they involve some new ideas. And number 3, as I said, is Thomas Huttinin, but he used a funny theorem which was obtained by Perry, Strel, and myself. And the theorem is that for any Calderon-Zygmunt operator, its weight, its norm in L2W is actually basically equivalent to its norm in the weak space. That's kind of a wrong formula because you have to add a joint operator, same thing, and you have to add M2, then it becomes the correct formula. And so this was the ingredient in the proof of Huttinin, and the second ingredient was sharpened random geometric construction. So, because it's extremely beautiful, I want to maybe say a couple of words about this sharpened random geometric construction. So, this sharpened random geometric construction gives a pretty fantastic result, lemma. So if T is a Calderon-Zygmunt operator, then there is a probability space such that T is equal So let me explain. So here epsilon is a certain positive number which depends on parameters of this operator. M and N are positive integers. And this letter is a Russian letter sh, which somehow is the first letter of the English word shift. So these are operators. It's a decomposition of the operator into the operators which are called shifts of complexity Mn. And so shift of complexity Mn is the following operator. So you have, first of all, it's dyadic shift. So you should have dyadic lattice. Then you should sum over all elements of dyadic lattice. And here, you should sum over all i's which are inside L and all j's which are inside L, dyadic of course, such that the distance, dyadic distance from I to L is m, the dyadic distance from J to L is n, and then you have coefficients C L L I J, F H I, H J. So let me explain. First of all, I write the formula only in one-dimensional case. So this is R1. Everything is exactly the same in all RD and actually in all metric spaces with doubling. But for simplicity, I wrote this formula. So let me explain what is HI and HJ. So for each dyadic lattice, for each dyadic interval, you have higher function. So higher function is a function which is plus constant, say, on the right half, and minus certain constant on the left half of the interval. So in particular, this function is orthogonal to constants. And it deserves this name if it's also normalized in L2. Okay, normalized in L2. So these guys basically are orthonormal bases, give orthonormal basis up to constant function. And if you consider it on the whole real line, it gives orthonormal basis. On the fixed interval, you just need to add constant function. So this is hard functions. And I need to say what are the conditions on the C. And these guys have the following normalization: square root, square root. So such operator is called dyadic shift. What does it do? It takes the energy, so you take L, go m generation down, take the energy from the mth layer, and throw it to nth layer. Okay, it just moves the energy from one layer of hard functions to another. So it kind of moves the energy from frequencies 2 to the minus m to frequencies 2 to the minus m. This is a hard shift. And the theorem says that...
Coefficients C, do they contain additional randomness? Or the whole randomness is in script D?
Yeah, of course. These are random shifts. So what it says here, that you will have a probability space of random dyadic lattices. So here it doesn't say anything. It just says that you have a random shift such that there's convex combination, because this can be considered as a convex combination. Right? So you have dyadic shift such that, well, this and this can be considered as a convex combination, so such that they give you your operator. But in fact, the proof is more concrete. This dyadic shift is really constructed by this random dyadic lattice, which is still on the blackboard. It's not the first model when you can use two independent dyadic lattices. It's the second model when you have to use probability space whose element is one random dyadic lattice. Well, of course, I wanted to present the proof of that, but it doesn't allow me to say anything about stochastic optimal control. The proof is very simple. You exactly do what we did before. We consider all dyadic lattices, decompose over each dyadic lattice your operator, as we did before. And before I said, let's not consider bad guys, because we can bootstrap. And here I shouldn't say that. I said, let's consider all of them, good and bad. But let's write, for every dyadic lattice, there are billions of them, because you see how many, 2 to the n at least, right? So for each d-adic lattice, we write the composition. It will have good and bad guys. Next line, next line, next line, and then add. And then divide by the number of lattices. And then the guys which will contain bad, if you compute correctly, they will pick up very small coefficient in front of them. So all guys where any badness will be present will pick up very small coefficient. So if you choose now n larger and larger, it will just collapses, and there will be no coefficient, and you will be left only with good guys. So actually, in this random geometric construction I explained to you, a certain inequality was involved. And here there is no inequality. It's just equal, equal, equal. It's algebra. And it works. Okay, so okay, now to finish, let me just maybe say about this proof, because the tool turned out to be very, very useful, independent of the fact that in 10 years there are several different proofs of that. But the proof itself, or ideas of the proof, turned out to be quite useful. And in particular, let me mention that this, say, proof of Hüttenin, which is based on ingredient of this Paris Trial Volberg, it's a very long and difficult proof. It's like maybe if you add everything, it's like 70 pages difficult. But using the ideas from here, you can make the same conjecture for any Calderon-Zygmunt operator, proved like in 7-8 pages. So this stochastic optimal control is useful. So if you unite stochastic optimal control plus random geometric construction, it gives some shortcuts. It helps. So this is why I want to say a couple of words. So of course the subject is not well suited for a couple of words, because stochastic optimal control is a very big and beautiful subject. But just let me give some small idea. So this, strangely enough, was proved by this method. And the main ingredient was to have function to have certain function of 6 real variables. Of 6 real variables, which is, is also parameter. And the function, first of all, is defined maybe I will write something. So the function is defined in such domain. The function b is non-negative, and some absolute constant times q. Over x plus 1. And the third property is the most important. Maybe just write equal to 0. So here alpha is just this vector, and HB is the Hessian of function B. Something stupid. So it's alpha 1, alpha 2, alpha 3, alpha 4, alpha 5, alpha 6. But here I want only alpha 3, alpha 4. Okay.
Hessian is symmetric.
What?
Hessian is a symmetric operator.
Hessian is a symmetric thing, yes. Hessian is just the matrix of second derivative. Now I want to so if people see such thing, supremum of alpha, then a certain expression, you see, it should be in omega. It's a PDE. Did you notice that it's a PDE?
What is PDE?
This third line is a PDE. The third line is
including the supremum.
Yeah, but it's a PDE. It's a nonlinear PDE. Why it's a nonlinear PDE?
Because you differentiate.
Because I differentiate, but this is a linear thing in derivatives. But it's nonlinear PDE because here x is, well, not x. How to denote these 6 guys? Z.
No.
Z. So Z is in this domain if I fix Z, I have to find alphas which give supremum. And it's a quadratic thing on alphas. So to give supremums, I take these quadratic things on alphas, take their derivatives in alphas, all coefficients depend on Z, I find stationary point in alpha, and feed them back. And when I feed them back, all this linear becomes extremely nonlinear. So actually what is written is a nonlinear PDE on second derivatives of HB, of B. And when people see such expression, f alpha x plus Hessian, or sometimes a little bit more involved expression, but depending on Hessian, they immediately recognize that this is what is called the Jacobi, Hamilton-Jacobi equation or Bellman equation from stochastic optimal control, Hamilton-Jacobi or Bellman.
What is controlled here?
Alphas are controls. So for each state x, which is Z, our 6, we're in phase space, 6-dimensional phase space, we are finding for each of them, we find the best alphas. And actually it gives us a vector at this Z. And then we have the vector field, which actually very geometrical.
Stochasticity.
Yeah. So stochasticity is not here because stochastic optimal control is a stochastic differential equation with control for which, for solution, you want to find the extremal. So you want to find the solution such that it extremizes a certain functional. So these are so there is a certain stochastic differential equation. Dx is
So you want to find it for every omega. You want to find it for every omega.
No, we want to find the control process alpha, which will give the best average, the best average gain, and it's just a control statement. So if you would have not a stochastic differential equation, but the usual differential equation, you again come to the question of control and extremizing a function. There are like 200,000 books about that. And the same with stochastic differential equation. So you want to maximize kind of your average profit along all lines of life. And it's of course you can do naively. You choose one control, compute solution, put it here, integrate, choose another control, compute, integrate, choose third control. There are many controls, as many as functions and even more. So you do it forever, but there is a clever way. You don't need to choose any control. You can compute your maximal average profit by solving a certain PDE. And well, of course, there is an explanation how to come from the problem on the right to the problem on the left, and this is what Bellman did. So if this is f alpha x, that will exactly this extremal problem. And sigma some special matrix, so speciality of sigma is reflected in this expression.
But where is Wiener process here? Wiener process, where is here? What I don't see is
Here there is no process. You see that the beauty of Bellman that he takes an infinitely dimensional problem of choosing continuum of processes and choosing one after one, which is completely unrealistic. He replaces it, but completely forgetting about that. In this problem, there is no probability, no processes, and it's finite dimensional. It's six-dimensional in this case. In general, it will be whatever dimensional, what are dimensions of guys here. So the only problem that it's nonlinear. And so the interesting thing that Stephanie and I, we used the existence of such functions. So we proved the existence, but we have no idea what is the formula. Well, maybe Stephanie knows now, but I don't. So the real solution of this thing, we never solved it. We never wrote the formula for the solution. We have no idea. Well, I have no idea how it looks like.
What about uniqueness?
It's very complicated in these situations because these are nonlinear equations, and the uniqueness and all these questions in Bellman theory are really subtle. The people write the books about that. So, but we don't need. We just need to construct one function with these properties, and we did. So we constructed such a function. And from here, we somehow, from the existence of this function, we somehow prove that alpha is Berling has linear estimate. Now, in other harmonic analysis problems, you shouldn't use this function. You should take your problem and find what functions you need then prove existence, and then you will have a certain harmonic analysis inequality. Because it has something to do with often with Monge-Ampere equations, there is a big suspicion that it can be maybe formulated on the language of carrying the measure. But as far as I know, I never really saw what is the problem of this type of measure carried from one place to another with minimizing certain functional. I never saw the direct connection between these two things. The only connection that this equation happens there and here, and so
You mean transportation of mass?
transportation of masses, right? Well, in a certain sense, you start with F, you finish with TF, so both guys have masses. They're not equal. You won't just estimate one via another. So, but I have no idea. So that's just speculation. Okay, so thank you very much.